Open on the. All right, everybody. So where we left off last class was talking about molecular polarity. Okay, so we didn't start this section. We actually finished off talking about molecular geometry. So just to review, you have to be familiar with what a steric number is, hybridization, molecular geometry, electron geometry. We went over the difference between molecular geometry, which considers only bonds, and then electron geometry, which considers bonds and lone pairs. We went over that last class. And I know that in general chemistry, you covered all kinds of molecular geometries like octahedral and square planar and square pyramidal and trigonal bipyramidal and seesaw. Okay, none of those geometries come up in organic chemistry at all. The only molecular geometries that you are going to need for organic chemistry are the ones that are shown right here. So the ones that are shown here. So you need to know the tetrahedron, trigonal pyramidal, bent, trigonal planar, and linear. Those are the ones you need to know for this class. So now what we're going to do is we're going to take the concepts of molecular geometry and we're going to add a little something to it. We're actually going to look at the bonds and we're going to say, is this bond polar, non-polar? If the bond is polar, we're going to draw the dipole, and then we're going to be able to determine whether the molecule is polar overall or non-polar. So let's get into that. So molecular polarity, and again, we're still in a review of general chemistry. So this is a concept that you would have seen in general chemistry 1. So going back to the idea of what electronegativity. Remember, electronegativity shows you the differences electronegativity differences result in what we call a polar bond. Just to kind of start us off here on a Tuesday morning, if you had a molecule like HF, right, you know that fluorine is more electronegative than hydrogen. Let me fix my lone pairs here. And what I told you last class is I said, if you're calculating the difference in electronegativity, we say delta En, the difference, delta, difference, En, electronegativity. We take the high number. So fluorine has an electronegativity value of 4.0, hydrogen is 2.1, and we end up with 1.9. Now that is a very strong dipole, okay? There's a very big difference, and you might say, well, that's greater than 1.7, so this must be ionic. But you remember last class, I told you that you have to take these values with a grain of salt, okay? Moses did not come down from Mount Sinai with, some rules about electronegativity. These are just things that were created by man. And so, yes, we can say the bond between hydrogen and fluorine is a polar bond, all right? So going back to this idea, it says here, induction or shifting of electrons within an orbital results in a dipole moment, okay? So if we were to draw our HF molecule, again, okay, we were to draw our HF molecule like this, we can represent the dipole a couple of ways. So I'm going to copy this and paste it over here because, like I showed you last class, there's two ways that we could represent the dipole. One way is to use the delta symbol, right? Who could tell me what the delta symbol stands for? Could anybody remind me what the delta stands for? No, the small delta, sorry, the little one. Exactly. It stands for partial or partially, right? Partially. You're right. The big one stands for change or difference in, but the little one stands for partially. So what this is saying, it's saying that the fluorine is partially negative and the hydrogen is partially positive. It's not an anion and a cation flat out, but we see that more of the electron density is on the side of the fluorine. There's an unequal sharing of these two electrons. One of the ways I describe it to my students sometimes is I'll say, I have 3 children. I have 2 daughters, and one of my daughters, she's only 3 years old, and sometimes her and I will go to Costco and we share a slice of pizza. Now, we do share it, but do you think it's equal sharing? I can tell you the answer is no. Okay, so even though we're sharing the pizza, it's not an equal sharing. And so it's the same thing that's happening here. The hydrogen and the fluorine are sharing those two electrons, but it is not an equal sharing, right? Electronegativity is defined as the ability of an atom to pull electron density towards itself in a bond. And what I have highlighted in green is a bond. And so the fluorine is pulling more electron density towards itself than the hydrogen is, okay? So that's one way to represent it is with the little delta, so delta minus, delta plus. And another way that we can do it is just to draw an arrow, okay? We draw an arrow like this, and then we put a little cross down by the side of the atom that is less electronegative, okay? Now that is what we call a vector. And vectors are very handy because they can help us determine the overall dipole of a molecule. So what we call a dipole moment can be calculated. And it says here the dipole moment is equal to the amount of partial charge times the distance between the delta plus and the delta minus. Now, you will never be asked, and this is going on the internet because I'm recording this, okay? You will never be asked to calculate a dipole moment in this class. Our textbook shows you how to do it, but I'll never ask you to do it, okay? What I want you to know is that dipole moments are measured in units of debye. Okay, that's just the unit of it. It's capital D debye. And a debye, you can see the definition is shown here. Don't worry about that. Like I said, I'm not going to ask you to do any calculations. All I want you to know at our level is that the greater the number of debye, the stronger the dipole, the more polar the bond. That's all there is to it, okay? So let me show you here. So going back to the two models that I was showing you before we started the lecture today, this molecule here, this is called dichloromethane. So this is dichloromethane, come on you, methane. Now again, the name isn't important. We haven't started nomenclature yet. But dichloromethane, you can see that there are two polar bonds in the molecule. There's one between the carbon and the chlorine, and another one between the carbon and the chlorine. Remember, the bonds between carbon and hydrogen, those are not polar, right? The difference in electronegativity between carbon and hydrogen is only 0.4. It's less than 0.5, so it's not a polar bond. So if you think about, if I have something pulling in this direction, and if I have something pulling in this direction, what's the net direction of those two dipoles, okay? The net dipole moment is going to be this one right here. So overall, we would say that dichloromethane is a polar molecule. If you take a look at ammonia, and you guys should all know the name of ammonia by now, okay? We know that nitrogen has an electronegativity of 3.0. Hydrogen is 2.1. The difference is 0.9. And so there's a dipole between the nitrogen and the hydrogen. There's one going this way, one going this way, and one going this way. Now, something that you may or may not have heard in your general chemistry class is when we have a lone pair. So this is a lone pair of electrons. It creates a small dipole as well. And so the dipole is going to go in the direction of the lone pair. So if you tally up those four vectors, you get a net dipole going in this direction. So is ammonia a polar molecule? The answer is yes. Okay, we'll take a look at one more, and it's a water molecule. And with water, now we know that water has a tetrahedral electron geometry and it has a bent molecular geometry, but you have four dipoles, and if you tally them all up, you get a net dipole going in this direction. So is water a polar molecule? The answer is absolutely. Water is a polar molecule. Now, you'll have to just bear with me here for a second. So if I go here, joys of teaching remotely. All right, so let me just turn on my camera here for a second and I'll demonstrate this. So, and again, this is what we were talking about before I started recording, okay? So this is a molecule of CH2Cl2 dichloromethane, right? We have a polar bond here between the carbon and the chlorine. We have another polar bond here. The bonds between the carbon and the hydrogens, which are the hydrogens are the white spheres, the carbon is the black, the chlorine is the green. Those are nonpolar bonds. So it doesn't matter how I hold it. It might be helpful if I hold it this way. You have a polar bond going this way and a polar bond going this way. So the net direction of the dipole is going to be going straight up from the way that I have it held. Okay, imagine if one of us, if I have a finger pulling this way and if I have another one pulling this way. Well, the carbon is down below. So if I pull, you see how it's going straight up like that. So it shows you the net direction of the dipole is going straight up. If I demonstrate the same thing with my ammonia molecule, so this is NH3. Here's the lone pair. That pink lobe represents the lone pair. I have a dipole going up this way. I have a dipole going up this way and up this way. So if I have three things going in the same direction, right, they're going to be going straight up. And then I also have the dipole on the lone pair. And so you can see that the net dipole in ammonia is going to be going straight up like that. Now, I don't have a model of water, but I can make one really quickly if I just grab another lone pair here. So if we just imagine the red atom is now an oxygen, and I put a second lone pair in there, this would be a model of water, right? Water has a bent molecular geometry. Oxygen is the second most electronegative element in the whole periodic table. I have a dipole going this way towards the oxygen. I have a dipole going this way towards the oxygen, one going this way towards this lone pair, and one going this way. So if I tally all four of those up, the net direction is going to be going straight up like this. And so water is a polar molecule. Okay, now one example that I didn't show is this one here. It's not on my slides. This is methane, CH4. It's the simplest organic molecule in the universe. Could anybody tell me methane, if you can't see it with my finger here, that's a white sphere too. Would methane be a polar molecule? Yes or no? Could anybody answer that? It's not, and it's not a trick question. I would never try to fool you. Right, Jenny says no. She's absolutely correct. It's not a polar molecule. How do you know that? Because there's no polar bonds in this molecule whatsoever. None, okay? There's no polar bond between carbon and hydrogen. Therefore, this is not a polar molecule. Now, if I move it out of the screen just for a second, could you guys just imagine with me, imagine if all four of those white spheres, instead of hydrogens, imagine if they were fluorines, okay? So we have CF4. In that case, and again, it's not a trick question, if all four of these white spheres were fluorines, would this be a polar molecule then? And again, I'm not trying to fool you or trick you. Would it be a polar molecule in that case? So the answer is no, not at all. Okay, it would not be a polar molecule. If all four of these were fluorines, it would not be a polar molecule. Okay, you'd have four very polar bonds. Yes, very polar. But what happens is you have one going this way, this way, this way, and this way. They all cancel each other out. Imagine if I had two more hands and if I had two people pulling on these atoms, okay, what would they do? The dipoles would cancel out. So you can have very polar bonds in a molecule and the molecule be non-polar overall. Okay, there's many, many examples of that. So just because you have polar bonds in a molecule doesn't mean the molecule is polar. Okay, it's not necessarily true if the dipoles cancel. So let me go back here. Anyhow, I think I'm still sharing my screen. Maybe not. Here we go. All right, so let's get back to the slides here. All right, so hopefully that clears things up a little bit. So somebody asked me, how many polar bonds does it take for them to cancel out? It depends. It depends on the molecular geometry, whether it's tetrahedral, trigonal planar, or whatever, okay? It doesn't matter. It depends on the molecular geometry. There's no answer that's just like 1 or 2 or 3 or 4, okay? It depends on the situation. So you have to, in order to be able to determine whether a molecule is polar or not, the first thing you've got to be able to do is determine its molecular geometry. If you can't figure out molecular geometry, it's impossible to figure out polarity, right? If I was to draw water like this, okay, if I drew a water molecule like this, there's nothing wrong with this Lewis structure, nothing wrong with it whatsoever. However, it doesn't give you a clear picture of the molecular geometry, right? You have to know that water is a bent molecule in order to know that it's polar. If you were to draw it the way that I have on the left-hand side, it would look like the dipoles cancel, right? But they don't, okay? We know that they don't cancel. So this is where organic chemistry gets difficult. This is where chemistry gets difficult because you have to be able to look at a structure like this one and know in your brain that it's actually bent, okay? You have to be able to make that assessment. So would water have a different dipole moment if it were linear? Yes, it would have no dipole moment, right? You'd have one going this way, one going this way, and they would cancel, okay? That's what you could say. It would be non-polar if it was planar. All right. So sometimes we use something called an electrostatic potential map, which is this pretty diagram here, to help us see the different regions of electron density. So if you look at the scale that I have on my slide here, where it's orangey, where it's orange colored, that's where it's more negative, and where it's blue, that's where it's more positive, so electron deficient versus electron rich. So if we take a look at a molecule of chloromethane, well, we know that there's one polar bond in the whole molecule. It's the one between carbon and chlorine. Chlorine has an electronegativity of 3, carbon is 2.5, so it's a polar bond. And you can see that manifest in this electrostatic potential map where the chlorine is very orange, right? Because there's a lot of electron density there. And then the carbon is mostly blue. Why? Because it's very electron poor. We see that manifest in the delta minus and the delta plus, and we also see it with the dipole. So more than one way to represent polar bonds. So now let's take a look at some molecules here. And if you remember, what I told you was the small d, okay, for a dipole moment, it stands for debye, okay, debye. And all I asked you to know is I told you, you're not going to have to do any calculations, okay? It even says down here at the bottom, no calculations in Chemistry 3101. All you need to know is the greater the debye, the more polar the molecule. So if you take a look at the dipole moment of acetone, it's 2.69 debye. You would say it's more polar than chloromethane, which is 1.87 debye, okay? Now you don't have to memorize any of these values, but you would have to be able to assess that acetone is a polar molecule. Now, again, there's no polar bonds between carbon and hydrogen. There's no polar bond between carbon and carbon, and so the only dipole in this molecule is the one between the carbon and the oxygen. So there's clearly a dipole moment here, and so acetone is a polar molecule. Let's try another one. Chloromethane. We know that carbon always has 4 bonds. It has 3 to hydrogen and 1 to chlorine. So if I draw the Lewis structure, or sorry, the structure of chloromethane, I'll just draw it like this. I've got a hydrogen here. I've got my chlorine here. You know what? Why don't I put the chlorine at the top? It might make it easier. So I'll put the chlorine here. And then I've got 3 hydrogens. I've got 1 in the plane. I've got 1 in back. And then I have 1 out in front like this. Again, there's only one polar bond in this molecule. It's the one between the carbon and the chlorine. So you can see that this molecule has a dipole moment, so on and so forth. Now, if we take a look at something like pentane, pentane has no dipole. It's a dipole of 0, okay? So that means it's completely nonpolar, okay? Completely nonpolar, 0 debye. Now, why would that be? It's made of what 2 atoms? Carbon and hydrogen. The difference in electronegativity between carbon and carbon is what? 0, right? The delta En between these is 0. 0, and the difference in electronegativity between carbon and hydrogen is delta En is equal to 0.4. So there are no polar bonds in pentane. None. There's no polar bonds in it. So what does that mean? It means anytime you see a molecule made out of only carbon and hydrogen, it's nonpolar. You don't have to do any assessment whatsoever. So let's try this one more example that people seem to be a little bit confused on. If you take a look at carbon tetrachloride, right? Carbon tetrachloride. So 4 chlorines. Now, we just said a few seconds ago that the bond between chlorine and carbon is a polar bond. But could anybody tell me, sorry about that. Sorry, there we go. Anyhow, where was I? Shoot. There you go. Sorry about that. Somebody trying to call me, I guess. Anyhow, so where was I? So we know that there are polar bonds in this molecule. Okay, there are polar bonds in this molecule. But could anybody answer me like in just a quick way and tell me why is this molecule nonpolar? And again, it's not a trick question. It's not because of the geometry. It's because the dipoles cancel. Exactly. It's because the dipoles cancel. So if we draw the dipoles, there's one in this direction, one in this direction, one in this direction, and one in this direction, and they cancel each other out. So dipoles cancel. So we could write here, dipoles cancel, therefore nonpolar. So like I said before, you can have polar bonds in a molecule and have it be a nonpolar molecule. So again, what's the kind of Sparks Notes version here? It says, understand the concept and definition of a dipole moment. You don't have to do any calculations. Understand the concept of a molecular dipole moment. So you have to understand what a polar bond is, and you have to be able to assess whether a molecule is polar or not by looking at its molecular geometry and assessing the dipoles within that molecule. So if we take a look at these examples here, it says identify whether each of the following compounds exhibits a dipole moment. For compounds that do, indicate the direction of the net molecular dipole moment? Well, if we take a look at this first compound here, okay, you can see that they didn't give us a molecular formula like C2H6O, okay? They actually gave us some information. They said first there's a CH3, then there's an oxygen, and then there's another CH3. So that gives us a clue as to the connectivity or how the molecule is connected. So how many bonds does carbon always have? Can anybody answer that? If carbon is neutral, it has how many bonds? 4, exactly. So we're going to put a carbon with 1, 2, 3, 4 bonds. Then we have the oxygen in the middle. Okay. Now, how many bonds does oxygen always have when it's neutral? Think of a water molecule. How many bonds does oxygen have when it is neutral? 2, exactly. Okay. It's got 2 bonds. Aaron, can I ask you another question? When an oxygen atom is neutral, it has 2 bonds and how many lone pairs? Again, think of a water molecule. Oxygen, when it's neutral, it has 2 bonds and 2 lone pairs. Exactly, 2 lone pairs. So now we have our next carbon, and it's got to have 4 bonds. So now you can see where I'm going with this, that you've got to fill in the hydrogens. And so this is our Lewis structure, okay? This is our Lewis structure. All right. Now, does the Lewis structure show us the molecular geometry? The answer is no. Okay, I've just written a Lewis structure. It shows no bonds going in or out of the page. But I want you guys to help me out with part of this. Can you guys tell me what the molecular geometry of both of these carbons are? They both have 4 single bonds. Think of what we talked about yesterday in class. What's the molecular geometry of each of these carbons? They're both tetrahedral, aren't they? Exactly. They both have 4 single bonds. So they're both tetrahedral. Now, the bond between carbon and hydrogen is a nonpolar bond. So I don't even have to worry about those, okay? Those are nonpolar. What about the bond between carbon and oxygen? Is that a polar bond? Absolutely it is, right? Oxygen has an electronegativity of 3.5. Carbon is 2.5. The difference is 1. So this is considered a polar bond. Now, I have another question for you. Could somebody tell me what the molecular geometry of this oxygen is? It's got 2 single bonds and 2 lone pairs. It's bent, exactly, just like in water. Water, the oxygen has 2 single bonds and 2 lone pairs, and therefore it is bent. So now what we're going to do is, if the molecular geometry is bent because of the 2 bonds, but it's got 2 lone pairs, that means its electron geometry is tetrahedral. So now I'm going to draw a representation of this molecule where I'm going to put this bond down here, this bond down here, and I'm going to draw 1 lone pair going in the back and 1 lone pair, one lone pair coming out in front, like this, okay? So remember, it's bent because bent, the molecular geometry considers the bonds only, but remember the electron geometry considers bonds and lone pairs, so it's tetrahedral, okay? So now I'm going to scribble in some dipoles, okay? Get my red pen. I've got a dipole between the carbon and the oxygen here. I've got a dipole between this carbon and this oxygen. Then I've got a dipole going in the back, okay? And I've got a dipole coming out in front like this. So is this a polar molecule? Yes or no? Could anybody answer that? And again, there's no trick questions in my class. Do those dipoles look like they're canceling each other out? No, they're not. They're exactly. Thanks. It's definitely a polar molecule, isn't it? Yes, the net dipole is going to be in this direction. Okay. And this is what makes organic chemistry tricky, right? Because somebody might look at this and say, oh, this molecule is nonpolar. There's a dipole this way and a dipole this way. They cancel, done. Okay. No, not at all. Okay. You have to be able to look at the molecule. I'm not going to tell you every time. You've got to be able to look at this oxygen, say the molecular geometry is bent. These 4 dipoles do not cancel. Okay. And so we end up with a polar molecule like that. Let's take a look at, I'm going to skip D in the interest of time, and I'm going to take a look at J with you guys. I think J is a little bit faster, okay? So let me ask you, in this molecule, are there any polar bonds in here? And again, I know I'm rehashing the same old concepts, but hey, we're learning the subject. Are there any polar bonds in here, in this molecule? Are there any polar bonds in here? Yes, absolutely. Thanks, Raul. Yep, we have two polar bonds, don't we? Okay, we have a polar bond going in this direction. Okay, so we have a polar bond going in this direction. Let me erase that. I'll fix it. We have a polar bond going in this direction. And then we have a polar bond going in this direction. Those are the only polar bonds in the molecule. Okay, so there are polar bonds in here. But is this a polar bond? Or sorry, is this a polar molecule? Yes or no? Absolutely. Okay, you would say molecule is non-polar since dipoles cancel. Dipoles cancel like that. There we go. So just give me 1 second here, everybody. I'm just building a model here quickly. All right, so if you're struggling with this, it might be wise to get a molecular model kit to help you, okay? So if you take a look at the molecule that we drew before, okay, dimethyl ether, so that's this guy up here. It erased when it didn't save the PDF, okay? But if I just redraw what I had drawn before, we have our carbon and our hydrogen, this, okay, and we said that the molecule was polar because it has a bent molecular geometry. We have a dipole going in the back, and then we have another dipole coming out in front like this. So we have a dipole here, dipole here, dipole here, dipole here. So those do not cancel each other out. Our net dipole is in this direction. So if I go back, bear with me, if I go back here, come on, no, there we go, okay. Son of a gun. All right. So if I turn my camera on, okay, so this is that molecule, dimethyl ether. So okay, here's the molecule. Can everybody see the molecule? Okay, cool. All right, awesome. So this is dimethyl ether. Remember, the carbon-hydrogen bonds are nonpolar. We don't have to worry about those. But the carbon-oxygen bond is polar. So there's one going up this way and there's one going up this way. Imagine you had two cars and then they crash at an angle like this. Which direction is the wreckage going to go? It's not going to stop like this, right? It's not going. They're going like this. So the net direction is going to be up. So we have one going like this and one going like this. So the net direction is up. Then you have a slight dipole here and a slight dipole here. If I pull those two, right, it's going to pull in the up direction. So what's the net direction? It's going up here, up here, up here, and up here. So the net dipole is going to be going straight up like that. And so that shows why dimethyl ether is a polar molecule. Anyhow, I hope that clears it up a little bit, but we got to move on. So let's get into intermolecular forces. Like I always say, what's it like teaching chemistry? You wake up in the morning, brush your teeth, and you talk about intermolecular forces until you go to bed, okay? Why do I make that joke? It's because any chemistry class that you take is going to involve intermolecular forces to some degree. Now, this is something, again, that you should have covered in General Chemistry 1. But if you think about properties like density, solubility, boiling point, melting points, refractive index, et cetera, those are affected by the attractions between separate molecules, okay? Why does water have such a high boiling point? Water is a tiny, tiny little molecule, but it's got this really high boiling point of 100 degrees Celsius. Well, you guys should know by now that the reason why water has such a high boiling point is because of hydrogen bonding. You know, there's a delta minus on the oxygens and there's a delta plus on the hydrogens. And then there's a force of attraction between the two dipoles, which we call a hydrogen bond, and that gives water its very, very high boiling point. So what are the intermolecular forces that you need to be aware of for this class? There are three of them. You need to know the London dispersion force, okay, which we sometimes just call London forces. These are the weakest ones, so weakest, okay? Then you have to know dipole-dipole interactions, and you also have to understand hydrogen bonding, which is not a type of bond, it's just a type of intermolecular force, but it is the strongest of the intermolecular forces that we're interested in this class. So let's start with dipole-dipoles. And remember that we looked at this molecule. This is acetone or nail polish remover. We actually looked at this just a few minutes ago when we were looking at the chart of dipoles measured in debye. And we said, okay, acetone is a polar molecule. Why? Because there's a dipole between the carbon and the oxygen. You can represent it with a vector like this, or you can put delta minus by the oxygen and delta plus by the carbon. Now, if we have a bottle of acetone, nail polish remover, which is a liquid at room temperature, all the molecules are tumbling around each other randomly. However, all the molecules do have a dipole, and you see that in the electrostatic potential map of these three molecules of acetone. But even though the molecules can tumble around, so this one can tumble around, you know, inside the bottle because it's a liquid, but what's going to happen is either the negative part is going to align itself next to the delta positive part of another acetone molecule, or the delta positive on the carbon is going to align itself with the delta negative on another acetone molecule. So you see how these molecules, since they have a permanent dipole, that they are going to be attracted to each other, right? If there's one thing you have to know is that positive and negatives are going to attract each other. We call that an electrostatic attraction. Give me a thumbs up if you follow me on the idea of a dipole-dipole. Everybody with me on that idea? Okay, so what do you have to look for? You have to look for a polar bond in your molecule, and if the molecule has an overall dipole, okay, if it's got a dipole, then you're going to have dipole-dipole attractions, okay? So there you go. So it says here, the dipole-dipole attraction between acetone molecules, so this is, I'm reading down here at the bottom, increases acetone's boiling point and melting point, while molecules that look similar, like isobutylene, have lower boiling points. I'll just draw isobutylene here for you quickly. Isobutylene, we actually looked at it the other day. It's this molecule here, okay? So maybe I can make that a little prettier. There we go, CH3 and CH3. Okay, now look at this molecule very carefully, the one that I've drawn in black. I'll ask you a question. Are there any polar bonds in this molecule? The one I have drawn in black. Are there any polar bonds in here? No, absolutely not, okay? So again, if a molecule only contains carbon and hydrogen, those are the only two atoms in this molecule, carbon and hydrogen. Can you have a polar bond between carbon and hydrogen? No. If you have right, you cannot have a polar bond between carbon and carbon, and you cannot have a polar bond between carbon and hydrogen. So if a molecule is made out of only carbon and hydrogen, it is always zero dibye. It has no dipole. It is a completely non-polar molecule. So if I have isobutylene, what are the only two forces that are going to be experienced between two molecules of isobutylene? Can anybody answer that? If there's no dipole. This is going back to the recesses of your brain. Exactly. The only thing would be London dispersion forces. That's it. Okay. So I'm going to draw a line here because there's no polar bond in this molecule. And so it's not going to have a dipole-dipole attraction with acetone. So again, if we compare these two molecules, isobutylene, look at its boiling point. It's negative 6.9 degrees Celsius, but acetone has a boiling point of 56. Why is acetone so much higher? It's because it has a dipole in it. Its strongest intermolecular force is going to be dipole-dipole. Okay, it has dipole-dipole forces. Whereas this molecule, isobutylene, as you guys told me, the only intermolecular forces experienced would be London forces. Now, I have another question for you. If I go back to the acetone molecule, Between two molecules of acetone, do I have London forces between those two of those as well? Yes, absolutely. You'd still have London forces, but they're not as strong as the dipole-dipole forces. Okay, even water has London forces. Okay, everything has London forces, but it's not the strongest of the forces. All right, so hydrogen bonding is nothing more than an especially strong type of dipole. That's all it is. So don't throw anything at me or don't yell at me. Okay, I'm not the guy who invented the name hydrogen bonding because it is misleading. You think, oh, it must be something bound to a hydrogen. No, it's an intermolecular force. It's just a very strong dipole is all it is. It says it right here in my notes. Hydrogen bonding is nothing more than a strong type of dipole-dipole. Okay, and again, I get it. The word bond is misleading. But again, it says, or going back to the idea here, it says hydrogen bonding is the attractive force between a hydrogen bound to. So you've got to have a hydrogen bound to either a nitrogen, oxygen, or a fluorine. The way my office mate explains this is he calls it FON. In order for hydrogen bonding, you got to have FON, okay? So it means you've got to have a hydrogen bound to a fluorine, a hydrogen bound to an oxygen, or a hydrogen bound to a nitrogen. Again, the hydrogen has to be bound to one of these atoms. You can have a fluorine in your molecule and have no hydrogen bonding. The hydrogen has to be bound to one of these atoms. So if we take a look at two water molecules, I illustrated this earlier on this morning already. We show the delta plus on the hydrogen, the delta negative by the lone pair on the oxygen, and then this little dashed line, that represents the hydrogen bond. And again, you guys answered this for me already. I said, why does water have such a high boiling point? I think Aaron wrote, oh, it's because it's got hydrogen bonding forces, and those are the strongest of the intermolecular forces. He's absolutely right on that. But why does water have a higher boiling point than something like ammonia? Because ammonia, this is ammonia here, right? Ammonia has hydrogen bonding. You can see you have a bond between nitrogen and hydrogen. You have your delta plus, you have your delta minus. You can see this cute little hydrogen bond that somebody drew in there. The reason why water has a very, very, very high boiling point compared to the boiling point of ammonia is water is, and you've figured this out by studying General Chemistry 1 and General Chemistry 2, water is a very special molecule in that it has two hydrogens. It has two hydrogens and two lone pairs. Okay, so the hydrogen bonding can be maximized. You have the exact same number of hydrogens bound to oxygen as you do lone pairs bound to oxygen. So 1 to 1 is the ratio. Whereas if you look at ammonia, it's got 3 hydrogens and only 1 lone pair. So the hydrogen bonding isn't maximized in ammonia. Water is the only molecule in the universe where hydrogen bonding is maximized. Now, why do you have to be so good at intermolecular forces as an organic chemist? Something that I tell my students is I say, like all you guys are going to finish, organic chemistry this summer. What I would expect you to be able to do by the end of this chapter is you should be able to go up to a first-year student and kind of give them a little tutorial on London forces, dipole-dipole forces, and hydrogen bonding. Now, why is that so important? It's because hydrogen bonding never goes away. It's going to be important in this class, obviously. It was important in general chemistry. It's important in biology. It's important in biochemistry. And I'm going to get into that in just a second. But it says here that only when a hydrogen shares electrons with a highly electronegative atom, again, your hydrogen has to be bound to fluorine, oxygen, or nitrogen, can it carry a large enough partial positive charge to form that hydrogen bond. Right? The reason why hydrogen bonding exists only with these 3 atoms is what's so special about fluorine, oxygen, and nitrogen is that they are the most electronegative elements in the periodic table. So the dipoles are really, really strong. So now keep in mind that even though hydrogen bonding has bonding in the name, it says here that even though hydrogen bonds are strong, hydrogen bonds are still about 20 times weaker than a covalent bond. Okay, so they're nowhere in the realm of a covalent bond. Don't get to thinking, oh, it must be strong like a bond. No, it's not. Okay, but it is a strong intermolecular force. Okay, so it says here solvents. Now, something that we're not going to talk about a ton this semester in organic 1 are solvents, but in organic 2, we get into more detail on the solvents. But when you have a solvent, whether it's water or acetic acid that you have shown here, or dimethyl sulfoxide or diethyl ether. Now, I know you're all learning the subject. You might be looking at this slide and going, what the heck are these things, okay? All of these molecules are liquids at room temperature, and they all make good solvents. If you go back to your general chemistry days, what was the only solvent you ever talked about? Was water. You never really discussed any other solvent at length. But in organic chemistry, there's lots of reactions that don't work in water, okay? Water is a very bad thing for the reaction. And so these three molecules are just examples. They're just examples of solvents that we can use in organic chemistry. Trust me, there's all kinds of other ones, tens of them, okay? But we say that if a solvent can participate in hydrogen bonding, we call it a protic solvent. So we would say that acetic acid is a protic solvent. Why? I didn't mean to do that. Why is acetic acid a protic solvent? It's because it has a hydrogen bound to an oxygen. So it can participate in hydrogen bonding. Now, if you look at DMSO, dimethyl sulfoxide, I'll use green, okay? We say this is aprotic because, yeah, you do have an oxygen, but it's not bound to a hydrogen, okay? You have hydrogens, but they're not bound to fluorine, oxygen, or nitrogen, right? Same thing with diethyl ether. It's got a beautiful oxygen in it, okay? Right? There's an oxygen in here. You can't argue with that, but is there a hydrogen attached to it? No, right? And you're like, well, there's hydrogens in the molecule. Sure, but they're not attached to the oxygen. And so therefore, we call that an aprotic solvent. So if you're wondering, why do I need to know this? It's more for later on that sometimes I'll say, okay, well, you would want to dissolve this in a protic solvent. So you'd find a solvent that can participate in hydrogen bonding. And then other times I'll say, well, this reaction works better in an aprotic solvent. So you choose one that can't participate in hydrogen bonding. That's all there is to that. Now, if we take a look at these three compounds here, you might have looked at the slides already, or maybe you read the textbook, and I hope you did before coming to class today. But what do you notice about these three compounds? Okay, so we have trimethylamine, ethylmethylamine, and propylamine. They all have different boiling points. But does anybody notice what's the same between all three of these? And again, it's not a loaded question. They all have nitrogen. Yeah, that's one thing. Does anybody notice anything about their molecular formulas for these three compounds? So they don't all have a three carbon. They all have three carbons. But all three of these compounds have the same, exactly. Thanks, Jennifer. They're isomers, aren't they? So all of these compounds, so all are C3H9N. They all have the exact same molecular formula. So that means they're all isomers of each other, okay? Trimethylamine, ethylmethylamine, and propylamine are isomers of each other. So what does that mean? It means they're made of the same elements and the same numbers, but they have a different connectivity, right? They're put together in a different way. And you notice that they have very different boiling points, don't they? Right? Trimethylamine has a boiling point of 3.5 degrees Celsius. Then you crank it up to ethylamine, which is 37. Then you get all the way up to propylamine, which is 49. Could anybody tell me why the boiling point gets higher and higher? Even if you don't have to give me a long answer, but could anybody give me a hint? It has to do with what? I'll give you a clue. It's the title of the slide. Yeah, it's hydrogen bonding. Exactly. Okay. Now, it's got something to do with hydrogen bonding, doesn't it, Jenny? Right? You're absolutely correct. Now, if I look at trimethylamine, is there any hydrogen bonding in trimethylamine? Is there any hydrogen bonding in trimethylamine? No, exactly. Thanks, Raul. Thanks, Isaac. You're absolutely correct. Lauren, absolutely correct. Right? There's a beautiful nitrogen in here. I can't argue with that. But is there hydrogen attached to it? No. So there's no hydrogen bonding in here. Now, you can take the time to make the model if you want, but there is a dipole in trimethylamine. So this molecule has dipole-dipole forces. Dipole-dipole. And of course, it has London forces. Everything has London forces, and we'll get into those in just a second. But if I get over to ethylamine, you can see that I do have the opportunity for hydrogen bonding. And so this has got hydrogen bonding. It's got dipole-dipole forces. I'm just going to write dipole. And then it also has London forces as well. And you see that propylamine is a little bit higher in terms of its boiling point if you compare it to ethylmethylamine. Well, you've got two hydrogen atoms now, so you've got more hydrogens that are capable of hydrogen bonding, so it stands to reason that it's going to be a little bit higher. So I'm just going to copy and paste this. So I'll put this over here. Come on, you. There we go. All right, so there you go. So now you kind of got to be Johnny on the spot, always looking for molecules and say, can this molecule participate in hydrogen bonding? Yes or no. So we'll put up here high boiling point. We'll put down here low boiling point. All right, cool. There we go. So I know that a lot of you, not all of you, but I know that many of you have studied biology at the college level. And so if you've ever studied DNA and looked at the double helix in DNA, or if you've talked about things like alpha helices and beta pleated sheets with respect to proteins in a biology class, an alpha helix, so that's what's shown here. So this is an alpha helix. This is a peptide chain. Okay, why does it form the alpha helix? It's because of hydrogen bonding. So these are hydrogen bonds in here. And of course, the double helix in DNA. So this is DNA here. Why does it form the double helix? It's a result of hydrogen bonding. So you can see how somebody who studies biology, molecular biology, cell biology, how they have to understand hydrogen bonding very, very well in order to be, to have a full understanding of the subject. So let's move on to the last of the three intermolecular forces that we're interested in this class, and that is the London force. So if we have two molecules that are completely nonpolar, okay, let's say you have two molecules of methane, right? Methane is CH4. So if I put a molecule of methane like this, I'll try to be consistent in my drawings. Anyhow, if I have a molecule of methane like this, there's no dipole in here, so obviously this is a nonpolar molecule. If I put a second molecule of methane in here, obviously there is some force of attraction between these two molecules. Okay, if you think of something like, what's something that you would see in your everyday life that's nonpolar? I'd say gasoline is a good example, right? Everybody uses it. So gasoline is a nonpolar molecule, but it's a liquid at room temperature. It's not a gas, so that means the molecules must be attracted to each other somehow. And the reason that they're attracted is because of London dispersion forces. So even though the molecules are nonpolar, they can still have an attractive force. So the idea is this: it says nonpolar molecules normally have their electrons spread out evenly around the nuclei, so all the charges are balanced out. However, you know what my office mate says sometimes? He says electrons are like hyperactive children, okay? If you give electrons the chance to move, they will. So electrons are in constant random motion, always moving very, very quickly. So what does that mean? You know what? I'm going to put my hands for just a second here. I don't know if it'll help, but even if it helps one person, it's worth it, right? So, sorry, I'm just going to stop presenting here for just a second. Turn on my camera. So I got to build a nonpolar molecule here. So I'll make a molecule of ethane, something kind of straightforward. All right. Can everybody see my model? The model? Can anybody see my model? All right. Thanks, Vanessa. Thanks a lot. Okay. So this is a molecule of what's called ethane. So it's CH3. It's made out of only carbon and hydrogen. There are no polar bonds in this molecule whatsoever. Okay, everybody with me on that? All right. So where do London forces come from then? If there's no dipole in this molecule, where does it come from? So this is where I'm going to talk with my hands. So like I said, electrons reside over the entire molecule, and electrons are like hyperactive children. If you give them room to move, they will. Now let's say you have all these electrons moving all around this molecule. What it said in the slide is that normally they're spread out evenly all around the molecule, and they're balanced out by the nuclei, which are positively charged, and so everything is equal and there's no dipole. But you guys know enough about probability. If you've ever bought a lottery ticket, why do you buy a lottery ticket? Because you're like, there's a chance. There is a chance. Okay, that's why I buy them, right? It's my dream tax, all right? I always buy it and say, probably not going to win, but there's a chance, okay? So if we have all the electrons moving around, is there a chance that they could all be clustered in one side of the molecule for a split second? Is that possible? Is it possible that all the electrons could just bunch up? Kelly says, sure, I agree, right? It's possible, okay? It's not going to happen a lot, but it is possible. So if all the electrons are gathered up on one side for a split second, what does that do? It's going to create a delta negative on that side of the molecule, and it's going to render the other side of the molecule delta positive. Okay, it's like if you had 100 people running around a room. Okay, what are the chances that everybody's going to end up in a corner? Okay, it's, you know, let's say if everybody's blindfolded and running around a room, is everybody going to end up in a corner? Probably not, but there is a chance that it could happen. So that's kind of the way a London force works, is that you take a nonpolar molecule, there we go. You take a nonpolar molecule. Okay, this is a nonpolar molecule. This is called pentane. But you see that in an instance in time that all of the electrons happen to gather up on one side of the molecule. It's not for a long time. We say it's fleeting, momentary, short-lived, okay? It's temporary, okay? What do those words mean? It means not for a long time. But if all the electrons gathered up on one side, what does that mean? It means on this side, you've got a big old delta negative, and what's that going to do? It's going to repel the electrons on the other one, and then you get a delta positive over here, and then they're going to be attracted to each other. Now, is it going to last for a long time? No, it won't last for a long time. It's short. But if you average them up, right, if you have enough molecules, Avogadro's number of them, they start to be significant, okay? Give me a thumbs up if that idea makes even half sense to you. But you should read the textbook to be doubly sure about it. Awesome. Awesome. There you go. So again, fleeting, momentary, temporary, whatever. It's a temporary attraction between two molecules. And yes, London forces generally are quite weak. Okay, generally they are, but like any weak attraction, if you add enough of them up, they can be significant. Let me give you another quick example about what this is saying right here. Okay, it's a weak force of attraction, but if you have enough of them, they can add up to be significant. Have you guys ever heard of this stuff? Has anybody here ever heard of Velcro before? Sometimes you can buy Velcro shoes, you know. Anyhow, my son has Velcro on one of his shoes. Anyhow, so if you've ever looked at Velcro before, right, you have the little hooks and then you have the little fuzz, and then the fuzz gets attracted to the hook or gets stuck in the hook, right? If I asked you to pull apart a piece of Velcro that was 1 inch long, would it take very much energy to do that? The answer is no. Okay, it would take very little energy. But if I gave you a piece of Velcro that was a mile long and I said, I want you to pull this piece of Velcro apart, is that going to take a lot of energy? Yes. So even though the Velcro has an individually weak force, if you add enough of it up, it starts to be significant. And that's the way London forces are. Okay, motor oil is a nonpolar molecule, but it's a big enough molecule that you add up the London forces and they start to be significant, and it has a very high boiling point. So I'm not going to ask you anything about the feet of the gecko, so I'll leave this as an FYI if you want to read about gecko or insurance or something like that. Kidding. Anyhow, so London dispersion forces, they're the reason why nonpolar molecules with more mass generally have higher boiling points. And so what you see here is this molar mass increases, right? We'll put here high molar mass, and then we'll put down here a low molar mass, right? Why does the boiling point increase? It's because the length of the molecule increases, and so there's greater chance for interaction between the delta positive and the delta minus. It's just like the Velcro idea. A longer piece of Velcro is going to take more energy to separate than a shorter piece of Velcro. And then we also see the same thing here. So all of these molecules, so these all are C5H12, okay? All of these molecules have the same molecular formula, so they're isomers, but you notice that the boiling point decreases. So we'd say over here, high boiling point, high boiling point, and then down here, low boiling point. Well, like I told you, the more surface area you have, the greater the London forces are going to be. So what does that mean? It means if you have more branching in a molecule, you're going to have weaker London dispersion forces, right? So if you look at this molecule, it's got way more branches, right? You've got a central atom with 1, 2, 3, 4 branches. It's actually kind of spherical in shape, right? And we know that a sphere, if you remember your math, a sphere maximizes volume for minimizing surface area. And so there's a less surface area, and so there's going to be weaker dispersion forces. And then the methylbutane has 2 branches, or 3, I guess, and then there's just one long chain with pentane, and so it has a higher boiling point. So what's the take-home message? The more branching you have, the lower the boiling point will be. All right, so let's see if we can do a question here. Let's see, it says, for each of the following pairs of compounds, identify the higher boiling compound and justify your choice. So if we take a look at A, we just zoom in a little bit here. Could anybody tell me, will these 2 molecules have hydrogen bonding? One's an A. Yes or no? Will there be hydrogen bonding for these guys? And again, there's no question designed to fool you. The answer is no, right? There's oxygen. Yes, absolutely. There's oxygen, but the oxygen is not bound to a fluorine. And so you are correct. There's no hydrogen bonding. Now, is there a dipole in these molecules? Would there be a dipole in these molecules? Yeah, absolutely, isn't there? Yes. See, somebody gave me a thumbs up, right? Why do we know that there is a dipole in each one of these molecules? Because you know the molecular geometry around the carbon-oxygen-carbon bond, right? That is bent, right? That's a bent molecular geometry. And so these molecules have dipole forces, and they also have London forces, because everything has London forces. Now, it's asking us which one is going to have a higher boiling point. Is it going to be the one on the left or the one on the right? Which one would have a higher boiling point? It's going to be the one on the right because it has less branching. Absolutely. So we'll put here higher boiling point because less branching. Heck yeah. All right. What about these 2 in B? Okay, in B, we have 2 molecules that only have carbon-carbon bonds and carbon-hydrogen bonds. So for these 2 molecules, what are the only intermolecular forces that they can experience? The only thing. London forces, exactly, right? London forces are the only things these can experience because there's no polar bonds. So we'll put here, London, son of a gun, my blue pen. London forces only, okay? Now, which one is going to have a higher boiling point? The one on the left or the one on the right? The one on the right, exactly. Thanks, Raul, because it's got a higher molar mass. So we'll put here, higher boiling point because higher mass, right? There we go. Ooh, I like C. C is a really great question. Okay, so if I take a look at the molecule on the left and on the right, could anybody tell me, let's try to do this one a little bit quicker, which one's going to have a higher boiling point? Left or right? Yeah, it's the one on the right. Absolutely. Yeah. Why is that? What does it have? They both have the same molecular formula. Higher boiling point because hydrogen bonding. There we go. Hydrogen bonding. All right, great. Now keep in mind that this molecule has a dipole, right? Because it's bent. Okay, so they both have dipole and London forces. However, the one on the left doesn't have hydrogen bonding. And then the 2 last ones, they're both capable of hydrogen bonding. You can see that because you have an OH bond here and an OH bond here. So they both have hydrogen bonding, they both have dipole, and they both have London forces. Sorry, I'm experiencing some problems here. So we'll put this one higher BP because hydrogen bonding. All right, and then the last one, as I was saying, we have the ability to hydrogen bond here and here. Which one's going to have a higher boiling point, left or right? Yeah, thanks, Jennifer. You answered it while I was rambling on. You're absolutely correct. We'll just say higher boiling point because less branching. Thanks. So I'll put here higher boiling point because Mr. Dion, what are you doing? My iPad really doesn't like me. You know why? Because I'm left-handed. And it always, if my hand touches the side, it throws it off. Anyhow, so we'll put here higher boiling point because hydrogen bonding. Okay, and there's a higher power that doesn't want me to answer C and leave it on the screen, so I'll just leave it the way it is. So going back to the idea of, polar and non-polar, one of the axioms that you should have learned in general chemistry is when it comes to solubility, like dissolves like. So what does that mean? It means something that is polar is going to dissolve in something that is polar. So polar compounds generally mix well with other polar compounds. So if you think of something like ammonia, ammonia is polar. So that is why ammonia dissolves in water so easily, because they're both polar compounds. Okay, and we could go on. You could say sugar dissolves in water. Why? Because it's they're both polar compounds. And then it says here at the bottom that non-polar compounds generally mix well with other non-polar compounds, right? Like dissolves like. Now, I know you don't know nearly as many non-polar compounds as you do polar compounds, but an example would be, you heard me mention pentane earlier on. We actually looked at it a couple times today. Pentane would mix with something like benzene. And again, you just kind of have to take my word for it right now, but those are both non-polar molecules. Another example would be if you get tree sap on your hand, right? Tree sap is non-polar, and you can wash that off with gasoline. So those are both non-polar molecules. Anyhow, just another, maybe I could put that one on there, but anyhow. So it says here, we know it's difficult to get a polar compound like water to mix with a non-polar compound like an oil. This is why you cannot wash your hands with just plain old water, right? You can't wash your clothes with just plain old water. What do you need? You need a soap, right? You have to have some kind of soap in there. And if you've ever wondered, how does soap work? Well, where soap comes from is from the hydrolysis of fat. It can be animal fat or it can be a plant oil as well. But anyhow, if we take animal fat and we hydrolyze it, if you think about the way the pioneers made soap, is they took animal fat and they heated it up with lye. They ended up making molecules that look like this. So they hydrolyzed a triglyceride, and you end up with something that looks like a fatty acid. So it has a big hydrophobic group, which is your hydrophobic tail, which is shown here in orange. That is nonpolar. And then you have a polar head group. This is, I'll just write down the name. You don't need to know it for now, but this is called a carboxylate. Carboxylate. It will come up maybe later today. But a carboxylate, you see, has two polar bonds in it, and so it's polar. So you've got this molecule that's got a polar portion and a nonpolar portion. So how does that work to wash our hands and our clothes? Well, the way that it works is what happens is you put a bunch of these together. Okay, so this is just one, but on the next slide, the way they have it represented is it kind of looks like this. So if you're confused, right, they have the green part, and then they have the long tail on the end, which is the hydrophobic portion. Okay, so these two are the same thing. Okay, so you see here, here's the hydrophilic portion, and here's the hydrophobic portion in here. But if you put enough of them together, enough of these fatty acids together, they form a sphere, and that sphere, we call that a micelle. So what happens is that the oil and grease and dirt from our clothes or our hands or whatever, that goes inside the micelle, and then outside of the micelle, we have the polar head groups, and what do those interact with? They interact with the water. Now, these are very, very small. Okay, you can't see these with the naked eye or whatever. But what happens is that's how the oil and grease and dirt gets trapped inside the micelle. But then the water enables the micelle to be solubilized. Okay, and then it washes it down the drain like that. So now you know how a soap works, and that is the end of chapter 1. I am really struggling with this thing today. There we go.